Geraint is a postdoc with Jack Burns' team, and his talk is entitled "Watching the Cosmic Dawn from the Moon: How and Why."
Right, thanks very much, Greg. Yeah, so Steve talked a bit about the physics, this 21 centimeter line. Abby's talked about a particular experiment, so I'm going to be concentrating on exactly how, given the data from this experiment, we actually go about extracting the physics of the cosmic dawn from those data, and then why we would do that from the moon and how that helps us. So the problem is that the signal that Steve and Abby have talked about is buried in very strong astrophysical foregrounds, and then it's filtered through this very complicated instrument, which Abby showed some pictures of, which has multiplicative effects on the foregrounds, and small multiplicative effects can obviously wash out this little signal. But we wish to extract the properties of the 21 centimeter signal despite that. So although you could take very many different approaches, our particular approach is to try and parameterize every possible factor going into the data, the 21 centimeter signal, the properties of the foreground, the properties of the instrument, and then go back and try and infer the values of those model parameters and the errors on those parameters. So the tool that we'll be using is called Markov chain Monte Carlo analysis. It's a very robust, very frequently used tool in cosmology and other areas of science. There are options and extensions that you can apply, but that's the kind of basic tool that we're going to be using for now. And to briefly go into why the moon is just a taster for the results at the end, the lunar environment actually simplifies this process quite a lot. So it provides us with a stable space environment, no rain, no wind, no variations in humidity or the amount of sun that reaches us. There are fewer complications arising from having to remove this strong radio frequency interference because we'll be around the far side of the moon. And not only do we have to avoid removing the strong interference, but what could be even worse is very low levels of weak interference, which can kill you without you even knowing it. We don't have to deal with the ionosphere, which is something that Jack and Abby have talked about on the Earth. It's a very big problem. It absorbs the cosmic radiation. It emits itself thermally. It refracts cosmic sources. We don't have to deal with that if we're in space. And we have a generic advantage of space is in that the whole sky is accessible to our missions. We want to have this very simple antenna which sits on the ground. It has no moving parts. But that means we don't get to point at anything. It just sits on the ground and points at the zenith. We only have a small amount of the sky available, whereas if we can see the whole sky, we can get lots of independent information from different areas of the sky. And so one of the aims of the analysis I'll just talk about here is to try and quantify exactly these advantages of being on the moon. So as I mentioned, we want to parameterize everything that we're interested in. So on the right, we see this familiar picture of the evolution of the 21 centimeter signal. Steve talked about the physics of it. Abby's outlined the experiment. So what I want to do is just try and encapsulate the shape of this signal in a few parameters. And what we do is use these turning points of the signal where the signal has either a maximum or a minimum. And we take the positions of these turning points as the parameters of our model, and the signal just evolves between them in some kind of spline fashion. So it turns out that it's not just completely arbitrary to use this parameterization. Jordan's going to mention how you can actually relate these turning points to the physics of the 21 centimeter signal, but I'll leave that for Jordan to talk about. And so the general framework we have is this Bayesian framework, where what we're interested in doing is inferring the posterior probability of some set of parameters theta from our data, given some hypothesis, which could be the hypothesis that the signal is well described by the turning points, or particular hypotheses about the properties of the first stars, or annihilating dark matter, or whatever. So we have parameters of the signal, the foreground, and the instruments. We have our data, which are calibrated spectra from DARE, and of course we use Bayes' theorem, so we can compute the probability of getting some data in some particular form, given values of the parameters and the hypothesis. We have some prior information on the parameters. And then there's this normalizing factor, the evidence, which it turns out we can actually use to compare different possible hypotheses. And that's a possible extension of what we do at the moment, but I'm not going to really go into that just right now. So, I mean, the general framework is this framework of Bayesian inference. And so what we do in particular is that we aim to get this posterior distribution of the parameters given the data. And in a sense, that's our entire knowledge about the parameters given the data that we have. So MCMC allows us to draw these unbiased random samples from this posterior probability distribution, even though we don't know it before we look at our data. And that will tell us, from that we can infer mean values of the parameters, errors, and so on. And so the way that the MCMC does this is to explore the whole parameter space with a random walk. So this parameter space can have a large number of dimensions, up to 86 in the models we're considering at the moment. So this is just a two-dimensional slice through that parameter space, and it shows a random walk taken by this Markov chain through parameter space. And this explores the parameter space, drawing these random samples from the probability distributions that we're interested in as we go. And it's an efficient way of exploring these high-dimensional parameter spaces. So the form of the data that go into our code, we have a small number of spectra from these different independent sky regions. So we collect data over time, the sort of waterfall plot that Abby showed right at the end of his talk. And we combine the data from these different times into spectra at low frequencies of a few different sky regions. Of course, our frequency range is 40 to 120 megahertz to try and encompass this interesting part of the signal with 3 of the particular turning points of the signal. And we aim that the spectra should have a level of thermal noise of order millikelvin for each of our spectral channels. Maybe half millikelvin up to a few millikelvin. And that's driven by the amplitude of the 21 centimeter signal, which is of order a few millikelvin up to 10 of millikelvin. And this corresponds to integration times of maybe hundreds of hours while we're in lunar orbit. So the various different contributions to the signal I've tried to summarize on this slide. The red line, it's a log scale. The red line shows a 21 centimeter signal, so part of the time it's emission, part of the time it's an absorption. But if you look at all these other foregrounds we have, some of them are many orders of magnitude larger. There's emission from our own galaxy, the sun, if we're not in the shadow of the sun, thermal emission from the moon. All the other foregrounds can be reflected from the moon and come back and come into our antenna from the back. And also, if we're not in space, if we're on the Earth, there's actually, I've got a line here for the ionosphere. That's still several orders of magnitude higher than the 21 centimeter signal. And particularly problematic is you can see that the shape of this ionospheric signal actually sort of mimics in some way the shape of the 21 centimeter signal that we're interested in. And that's why it can be a particularly insidious foreground. So the calibrated spectra look a bit like this. So by calibrated, I mean that we've compared them to these load spectra that we switch to during a phase of our data taking. And the reason they don't look like those nice, smooth power law-like things on the earlier slide is that they get filtered through this complicated instrument response, which then adds its own noise. Then we try and subtract out this load spectrum, which tells us something about the properties of our instrument. And so we end up with these different spectra from different areas of the sky, and those we feed into our code. We have models for how those spectra depend on our parameters, and then we try and infer the values of these parameters. So these are noisy spectra. You just can't see the noise because it's that low after this amount of integration. And the form of the results is that, so what I've shown here down the diagonal are one-dimensional posterior probability distributions of the frequency, temperature of turning point B, frequency and temperature of turning point C, and the frequency of turning point D. So these are one-dimensional posterior probability distributions from which we can extract mean values of the parameters and errors on the parameters. But we also get, if we look at our parameter space in different ways, project it in different ways, we can get two-dimensional joint distributions of any pairs of the parameters. So we can look at the correlations between the parameters, degeneracies between them. And it really allows us to look into what our, very much detail of what our data are telling us about the different parameters that we're interested in. But of course, we can also translate this into what it means for the signal itself. I'm showing the inferred value of the 21 centimeter signal in blue and compared it to the true signal which we input into our simulation pipeline, which is this dashed black line. So you can see the 2 sigma errors are in red. So you can see that we managed to recover this 21 centimeter signal. The errors are actually deceptively large because they're actually very highly correlated with frequency. But we actually extract the shape of the signal pretty well. You can see that if we can look at 8 sky regions for a space experiment, we can see the signal turn over here, which means we've really detected this turning point B. This is the turning point we think corresponds to the first star switching on. If we only have 2 sky regions, this turning point, you don't really quite see it quite so well. It's already showing the effect that having the whole sky available to us from space really affords us as a benefit. And to look at one of the other big bugbears of this experiment, the ionosphere, I've compared the results that we get without the ionosphere for the frequency of turning point B, again, these first stars. The vertical line here is the true value that we put in, so we recover that nicely. We have errors of maybe a couple of megahertz on this frequency. If we now try and do it without the presence of the ionosphere, it broadens out this posterior probability distribution. And in fact, we can't rule out this turning point line below 40 megahertz, which is the very bottom of our band, which means that we haven't really detected this turning point at all. So already this extremely simple model of the ionosphere really prevents us from fulfilling one of the goals of our experiment, really showing the advantage of going to the moon where we avoid all this. And for my conclusions, I'll just say that we aim to use these very robust, well-established inference tools to try and learn about the 21 centimeter signal using our DARE data. Even for idealized models, I think we can show that there are very clear and quantitative benefits of doing this 21 centimeter science from the lunar far side. The whole sky being accessible, there being no ionosphere, no radio frequency interference. And we're moving towards, of course, more realistic models of variable ionosphere, a temperature dependence of instrumental parameters, which we will have to cope with for our ground-based prototypes, and dealing with these time-ordered data. So I'm a bit over, but that's all I have to say. Thanks.
Okay, great. Thank you very much, Geraint. Really appreciate that. Great talk again. Let's see. I don't have any questions from here, and I'm not seeing anything online as well. I want to encourage everyone who's online now to ask questions. I don't generally think of astrophysicists and heliophysicists as a shy bunch, so please do ask questions in the presenter questions portion in that box on Adobe Connect. So Geraint, thanks again. Wonderful talk.